सादिया देखें आ गया लाइव उस पे फेसबुक पे आ जाना चाहिए। ये मेरे पास तो इंडिकेशन आ गई है फेसबुक की। हाँ जी। हाँ जी, अस्सलाम वालेकुम परवेज नशाई, वेलकम।
थैंक यू वेरी मच सर। वालेकुम सलाम रहमतुल्लाह। जाड़ों का मौसम मुबारक माशाल्लाह से।
शुक्रिया जी, शुक्रिया।
हाँ, कम से कम एसी से तो जान छूटी
Anwar is
होगी।
a very senior engineer also working in Saudi Arabia. Pervez Nashai with a very reputable organization. He is mostly doing soil investigation and nowadays pile foundations. बड़े he's experienced
या
engineer और innovative काम करते रहते हैं ये भी।
या स्वादी खा डॉक्टर साहब, स्वादी खा।
सॉरी क्या आपने
सो
इसका
दैट
मतलब आपका
वी
बैंकॉक चक्कर लगता रहता है।
जी जी दे नहीं, चक्कर तो 2 साल वहीं रहे ना। आई डिड
अच्छा अच्छा वेरी गुड।
मास्टर फ्रॉम अंडर बाला सुब्रमण्यम फ्रॉम
अच्छा अच्छा अच्छा
1992।
अच्छा जियोटेक
So,
में अच्छा माशाल्लाह।
Tahir Sultan sir, sorry to uh, talk in our Thai language to create AIT environment actually.
नहीं नहीं, ठीक है ठीक है।
That's
बस
a
अब मैं
fantastic
फॉर्मली शुरू
thing.
करने लगा हूँ। फॉर्मली शुरू करने लगा हूँ और इंशाल्लाह फिर
जी जी जी
मैंने कहा आप माशाल्लाह सीनियर इंजीनियर हैं, वो काफी करते
जी
धरते। डॉक्टर साहब से आपका इंट्रोडक्शन होना चाहिए।
जी जी
तो
thank you very much sir, thank you, so nice of you.
ठीक है जी,
So,
सादिया इज
where
ओके।
from Dr. Sahab, you are now addressing which department or you are
आई एम विद स्ट्रक्चरल इंजीनियरिंग डिपार्टमेंट जी।
sorry?
स्ट्रक्चरल इंजीनियरिंग।
Oh, structural engineer. That was, GTE and a structural engineer, we were
जी जी
together.
आई नो आई वाज देयर इन 1986।
Oh, you were there in 86 in structural engineering.
जी जी
Yeah, yeah, fantastic. So I was in Saudi at that time. Thank
अच्छा
you, thank you. We had fantastic structural engineers with us, top class structural engineer who did master in our session. And I was also member of the General Assembly, being a class representative. So
ओ
we
वेरी
become
जी
automatically member of General Assembly and, all those bit of
वंडरफुल
political thing as well.
बहुत बहुत अच्छा किया है वेरी नाइस।
Yeah, yeah.
जी,
आई वाज
आई
जी
एम गोइंग टू स्टार्ट इट जी फॉर्मली। इट्स 10 past 2 नाउ। सो डॉक्टर साहब जस्ट बिफोर स्टार्टिंग वो क्वेश्चन आंसर सेशन फिर हमारा आखिर में ही होता है 20 मिनट्स का। तो
जी
इफ देयर इज एनी पर्टिनेंट क्वेश्चन ड्यूरिंग द लेक्चर देन आई विल इंटरप्ट यू व्हेनेवर इफ आई थिंक इट इज पर्टिनेंट। अदरवाइज आई वुड
जी
लाइक कि आप
आई
कंटिन्यू
थिंक
कंटिन्यू
नहीं आई
फ्लो
थिंक
आपका कायम रहे।
नो प्रॉब्लम आई थिंक वी कैन जस्ट हैंडल द क्वेश्चंस एज वी गो along क्योंकि इतने ज्यादा पार्टिसिपेंट्स नहीं हैं तो आई थिंक विल बी फाइन।
हाँ जी, हाँ जी, ठीक है जी, ठीक।
लेकिन स्ट्रक्चरल इंजीनियर को जितने लग नहीं रहे लेकिन मेरी टॉक मोस्टली स्ट्रक्चरल इंजीनियरिंग पे है तो लेट्स सी।
अच्छा 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 अच्छा।
No, we want to learn, Dr. Saab, we want to learn structural engineering, definitely. So pile foundation and structural engineering goes hand in
जी
hand, and you will find good structural engineers there. Yeah.
चलें जी, इसको अब हम शुरू करें जी। Bismillahirrahmanirrahim. In the name of Allah, the most gracious and the most merciful. Ladies and gentlemen, Assalamu alaikum and good afternoon. On behalf of Pakistan Society of Civil Engineers, it is our pleasure to welcome all attendees, including those joining us via Facebook. Today marks the 85th installment in PSCE's enduring monthly lecture series, a tradition of learning and exchange we have proudly sustained since 2020. More than a calendar milestone, each lecture reflects our shared commitment to elevating civil engineering practice through dialogue, insight, and innovation. Whether you are an emerging professional or a seasoned expert, we invite you to engage with us in shaping PSCE into an ever stronger platform for knowledge, collaboration, and professional growth. Now, before I introduce to you the guest speaker and the topic, it is my duty to read out the rules set out by Pakistan Engineering Council for conducting a webinar, technical webinar. Participants registered for CPD points are required to appear live on webcam. However, female participants have an option to cover their faces if they wish while appearing live. To ensure a smooth session, the microphones of all participants except that of the speaker will remain muted throughout the lecture. A dedicated 20 minutes question and answer session will take place at the end of the lecture. Please note that questions during the lecture should be submitted via chat box only. At the end of lecture, I shall read the questions which the guest speaker will answer. And wherever I find it pertinent, I will interrupt and ask the question if I find it pertinent to be asked at that time. Participants joining us on the Facebook have the same facility of typing their questions in the chat box, and inshallah, I will read those questions and the speaker will answer them. Now, today's topic is innovative tools for enhancing engineering education, and our guest speaker is Dr. Naveed Anwar. Having his PhD from Asian Institute of Technology, Bangkok, Thailand, and master's also from the same institute, and with a bachelor's degree in civil engineering from UET Lahore, Pakistan, Dr. Naveed Anwar is a distinguished structural engineer of Pakistan origin. Serves as senior advisor to the president of Asian Institute of Technology and CEO of Computers and Structures in Bangkok. This computers and structures is abbreviated as CSI. At AIT, he is leading the establishment of pioneering School of Professional Practice, while also teaching graduate level courses in structural and earthquake engineering, coordinating academic programs, and mentoring research scholars. In his role as CEO, he oversees the development, mentoring research scholars. He is in his role as CEO, he oversees the development of advanced engineering software solutions. With a career spanning over 4 decades, Dr. Anwar has made significant contributions to teaching, research supervision, software innovation, capacity building, and the execution of major civil and structural engineering projects across more than 20 countries. His prolific academic output includes over 100 publications and the supervision of more than 50 master's and PhD theses. He has also conducted over 100 seminars and workshops reaching thousands of engineers worldwide. At AIT, Dr. Anwar has spearheaded transformative initiatives such as Asian Center for Engineering Computations and Software, AIT Solutions, iLab, and the AIT Share platform for online education. His leadership has extended to strategic collaborations with HEC Pakistan, capacity building programs in Pakistan, and partnerships with global institutions, including the Asian Development Bank, World Bank, and UNESCO. He also maintains active engagement with CSI's headquarters in California. Dr. Anwar's technical expertise encompasses finite element modeling, advanced concrete design, performance-based design of tall buildings, bridge engineering, and the integration of emerging technologies such as IoT, machine learning, and mobile computing into structural engineering practice. So this was a very brief introduction of Dr. Anwar. And Dr. Saab, the floor is yours. Please continue.
Thank you so much, Sultan Sahab. I think the introduction wasn't that brief. Thank you so much for your kind words. So let me share my screen. So please let me know if you can see it. So today, actually, I want to discuss about innovative tools for enhancing engineering education as well as the practice, because now, as we know that there is a growing gap between what is being taught at the universities and what is needed in the profession. So that's the main sort of thesis of this discussion. And then what kind of tools or what kind of approaches we can take to bridge this gap, and especially look at how the new generations will be learning. So first of all, let's start from, because this is a lecture where we have enough time, so I want to start at the beginning and see where we are heading and where we have sort of started, we have started our journey. Can I continue? Okay, so let me start at the start of the first agricultural revolution, some about 12,000 years ago, when the civilization really moved, into settlements, and then the second revolution, which was about 1700 years ago, and then after that, suddenly everything became very it expanded at a very fast pace. And then we have the first industrial revolution, then the second, third, fourth, and now we are talking about the fifth industrial revolution in a span of very few years. Because if you look at the development for 12,000 years, there wasn't much change in how things were done. But in the last few years, this has changed significantly, and especially, the rate of change has accelerated. And now you can see from each revolution is now coming at a faster pace with this smaller gap between the changes. And the last one is just about 20 years between the fourth and now the beginning of the fifth revolution. So we can see now that at such fast pace, anything that we have been doing in the past will not work in the future. It's even hard to project how things will work. So with that background, let's look at how the university education has progressed uh, during these five industrial revolutions. So we can see that the engineering was one of the first proper discipline to be established, followed by business, then entrepreneurship, computer science, and then now we have the startup and incubation thing. Of course, many other disciplines come in between, but I'm just picking a few important ones, especially relating them to the industrial revolution, because business became important because industry was flourishing, so they needed business studies to manage that. And now at the current stage where we have the generative AI and other things coming together, physical AI and many things, we actually don't know what form it will take. So that's the brief background of this discussion. But this, I think, is the more interesting slide where I have try to combine several factors together. First of all, is this new concept, as you know, of the calling every generation, giving them a name. So starting from the silent generation to baby boomers to Gen X, millennials, Gen Z, and then now Gen Alpha. And the broad lines are showing roughly their lifespan. And on top of that, I have also shown the educational or learning time span for each one of them. And then the professional span, the blue color, and the green color is the learning span. So what we are trying to see is that this generation, when they were um, learning and when they were practicing, what kind of technologies were there in terms of the development. So we put five technologies there: the arrival of the pocket calculators, the arrival of the personal computers, the introduction of the internet, and then the smartphones, and now AI. So these, each one of them is a kind of a milestone in the technological development, and they have changed way. And every time a new technology came, it was a resistance. When the calculators were introduced, people said, "Oh, we should not use them because then we will forget about the arithmetic." And similarly, when computer programs came, we had the same kind of a reaction. Now for AI, we have the same reaction. But what is interesting on this graph is that the current, we are now at this, the red line area, and the generations that have just started to learn or are just entering the profession, they are now in a very strange transition, because what they learn and what they're going to practice is very different. And the coming generation are going to start learning with no knowledge of the previous technologies. They have not experienced anything. Generations like mine or our colleagues, we have seen everything during our studies and during our practice. So we have a full understanding of how things were done and how they're changing, so we can adapt. But people who haven't even seen how things were done, for them, the present is the reality. So that's why the university somehow and our professions are unable to address this rapid change in the generations and rapid change in the way they are training themselves. So I'll come back to this slide a couple of times again. So now let's see, how does it relate to us as civil engineers and structural engineers. Now, as we know, that physical infrastructure is the backbone of any economy and this society. Nothing can work without the physical infrastructure. Everything that we do, all of us, is related to that. And uh, so that's the first important thing, that we are the pillars of the infrastructure is the backbone. And we as structural engineers are the one who handle this backbone of buildings, bridges, tunnels, dams, transmission towers, communication, power plants, expressways, industrial plants, and everything. Everything that is built is done by civil engineers. So which means our role is extremely significant and important. So whatever we do affects this backbone of the infrastructure and the society. So our decisions are very critical. Now, if you have seen this statement, I repeat this a few times before also. And this is a statement from King Hammurabi, which was around 4,000 years ago. And he was the first person who started to define what built environment was and what were the responsibilities, and make the first laws and first codes. And this is one of the clause from his codes, clause 229, which is, as you can read here, uh, clearly defines the responsibilities of the builders. Uh, at that time, no engineers, but it includes everybody. So now engineers are part of that group that has the responsibility to deliver uh, structures and infrastructure which is safe for the people. So this and the penalty was so severe. So we can see that the importance of our work was recognized almost 4,000 years ago, long before any math or any physics or any engineering was developed. Now, if we look at our role in the present day, we are looking at this equation where we are trying to, and this is the same concern that King Hammurabi had, that to prevent disaster. And disaster, now we know that is composed of hazard, vulnerability, and exposure. And out of that, the vulnerability hazard is not much in our control, and exposure is the work of the planners. And again, one not in our control as much as engineers, but vulnerability is very much our responsibility. So, which means that the risk of disaster is contributed by primarily the vulnerability or vulnerable built environment. And so the key role of structural engineer is basically to reduce disaster risk by reducing the vulnerability with due consideration to sustainability. In fact, I was telling my class that we should start calling civil engineers or structural engineers as disaster risk and sustainability engineers. And I'm sure if we call ourselves like that, we will get much more jobs and much more money, because a lot of funds are available for disaster risk reduction and for sustainability. And I think as civil engineers, we do exactly that. We just don't call ourselves. And I think if we start doing that, our role will be more prominent in the society. So the design of built environment has evolved from 4,000, 5,000 years ago to now, from intuitive design without calculation to code-based design, performance-based design, consequence and risk-based design, resilience-based design, and now AI and tech-assisted solution. So we are traveling this ladder. And during this time, we have the progression of our understanding of the mechanics, of the materials, methodologies, computations, and technologies, and much more. So, which means that we are now in a path of this progression, and this has become very, very fast at the moment. Since the intuitive design lasted thousands of years, the next phases are coming and going very, very fast. So, which means that we have to adapt the education and the practice. So let's look at now the education of engineers and the practice of engineering together, because we cannot separate them in the current context. Now, let me go back once again to the design of the Eiffel Tower. Eiffel Tower, as you know, everybody is familiar with the structure. I took this picture a couple of months ago. And this structure is named after the structural engineer, and one of the few iconic structures which is named after the designer or the builder. Also, he was a designer and builder. And the interesting thing is that this was done all by hand calculation, by graphical statics, and without hand sketches. There was no computers, there was not even calculators, there was nothing. And the what the students at that time were studying was exactly what they were doing. So there was no gap between education and practice, because both had no tools except understanding and hand calculations. So engineers design all these iconic structures with the same tools they learned in school, and zero gap at that time. Now, if you look at the about 50 years later, the Empire State Building was designed and built in 1931. Once again, at that time, before computers, before calculators, before any finite element analysis, we have very simple methods of Portal and cantilever methods, slide rules, and so on. But they did a little bit more work. They developed some special procedures for analysis and design, and mostly over-design things. So the graduates at that time needed 1 or 2 years of special training to design buildings of this kind. So the gap was there, but it was still very narrow, because once again, both the education and practice use the same methodologies. And these universities were the leaders because they were teaching these techniques. Let's come to the current stage of these buildings, of tall buildings now. And now you can see that we are using all kind of nonlinear analysis, wind tunnel, CFD, parametric modeling, optimization, digital workflows, and so many advanced tools and technologies are being used. And they are not being taught at the universities. They can't be taught at the universities for several reasons. So now we have at least 5 to 10 years gap in proficiency, because the tools that are used far exceed the university training. They are so advanced, they have methodologies in there which are not taught even sometimes at master's level. So which means that now the practice has gone far ahead and education is lagging behind, and this gap is now ever growing. And this is also true for an average structure, not only for tall structures, because those tools that are designed, used for the iconic structures are also available for every other building. So anybody who has access to programs like ETABS or SAP 2000 or programs like that, and they have the access to same technology as the people who are doing these tall buildings, because those iconic structures use the same tools as anyone can use. So which means that as average building, tools are available which are just as advanced as for the top level structures, but the education is clearly lagging behind. So the problem then is that the engineers spend more time learning the tools than doing the actual work. And they're always behind and they do not understand most of the technologies in those tools. So now the gap on average between practice and education has become quite wide. And universities try to address it by doing some training programs. But if we have seen even at AIT that our graduates after masters, they find it difficult to be prepared for taking up the assignments. So this is a summary of that. Within 100 years, we have created a huge gap between education and practice, or learning and practice, which means that the education, and this is just the beginning. I have many other things to talk about on this one. And once again, if you see now, these generations, new generations, are not even aware of all these technologies used earlier. And they are starting at a stage where many of our professions are ending, or our education ended long before the advent of these tools. So let's go into a little bit more detail. So the impact of these evolving technologies is that calculators reduce the need to learn arithmetic. As you know, we stop remembering tables. Now we have to, even to multiply a simple few numbers, we open the calculators. Computer programs reduce the need to learn procedures and solve equations. We all rush to the programs, even for simple problem, even for a simple beam, people start to use finite element programs. The internet reduced the need to read and remember. So because we know that we can always find the information. Smartphones reduced the need to engage with the physical world and provided everything on our fingertips. So mobility came in. And now AI is reducing the need to know and even to think, because now people rush to ChatGPT and other tools to get the answers and and to solve the problem for them. So it's now we are in a stage where we are uh, delegating a lot of our work that you used to do earlier to the tools and the technologies. So to summarize once again, the calculators liberated the engineers from slight rules, and then the practice became faster, increased the accuracy. Of course, engineers could do more design alternatives, and portable computation enabled field calculations. And so we all have gone through this one, how useful the calculator is, and how everybody would carry a calculator at some point in their pocket. Of course, now a smartphone has become that as well. So, but once again, the students and the practitioners have the same tools. And software, when that started, uh, the university started to teach programming in the universities. I learned Fortran. I'm sure many of you learned that on some language at that time. So we had some idea how these programs work, and many people started developing software. In fact, if you look at the software industry in engineering at this time, almost every major company, software company in engineering, is run by engineers themselves, and is staffed by engineers themselves. So that means engineers became programmers, uh, you know, very good programmers, is so much so that they started developing tools for other engineers to use. And then, of course, the practice, from the CAD to early finite element, simple ones, to all of these special programs is expanding. And now people develop in-house programs. I remember I was in Pakistan when I started my company in uh, I think it was 88 or something. I also started a software company at the same time called Technosoft. So we had engineering consulting and software development even at that time, because we needed tools to do our work, and we couldn't find those tools. So we started developing them and also trying to sell them. And with the World Wide Web, the people say that we have equalized the access to information, which is very true, because before that, people who have books, access to libraries, access to data, access to knowledge, could do bigger projects, better work, and those who didn't had a disadvantage. But with the internet, everybody had the same level of access to everything, and that really changed the sort of availability of information, and the learning of the the techniques. So that was really a major change, that everybody had the opportunity to to practice at the same level because of the internet and because of the availability of the software tools. So if somebody has ETAPS and has a good knowledge, has done the training, has access to internet, they can do the project the same as anybody else in the world. And that is a great advantage of having these tools and internet. And then, of course, smartphones further made it easier. So many things combined together. Now they say one smartphone typically carries 26 or 30 gadgets in it. So we now have a lot of real-time access to everything, and also gave us the mobility to work and practice anywhere and learn anywhere. But the biggest change now is coming from AI, and especially the kind of AI that we have now. the ChatGPT or the generative AI or the LLMs. And that is basically completely changing the way people work. The previous were step-by-step changes, but this one is it's a metaphorical change. And now it seems that this will disrupt so many things. And now people, I was telling my students now that now it's not necessary for you to learn procedures. It's not necessary for you to learn how, but the why. We have to focus on why we are doing something and why it should be done. What are the questions? Because the answers are there, but the questions have to be formulated. And that's why the prompt engineering is such an important field these days, how to ask questions. And if you know how to ask the questions, the answers are available. So which means the job of the engineers will become more on more deeper thinking and raising the questions. I give you an example of how these LLMs can provide explanation now. So this is a diagram. Many of you may know it. And if I used to ask the students in my class, many would not know, even though they have completed the bachelor's. But if I gave the same image to an LLM, then it will give you very detailed description just from the image of what it represents and all the understanding behind it. And this is such a major, I would say, tool for learning, because no matter how complex an image or a figure or a graph or a table is, you now have the ability to understand it simply by providing it to the AI tools and then ask them to explain what this is. And it's amazing that just based on this pixels, they can just see pixels and patterns. They can determine exactly what's going on here. And it's so accurately depicted. And this is a couple of years ago. So you can see now that the learning or education is now not dependent on what teachers teach. It's not dependent on what the books give. It's only dependent on the questions that we have. And we can basically learn almost anything instantaneously. And you can see here so many specific GPTs, as they say, have come, single for civil engineering, for college engineering and others. And these are all specialized tools built on top of the AI to provide engineers with learning capability. Let me show you a program that we have developed based on this AI concept, and this is for the design of a bridge. So the idea is that, let's say you are a senior engineer or a chief executive or a senior level person, and somebody calls you, or just an engineer, and somebody calls you and say, I would like to design a bridge of this length. Can you give me the best system, most economical system with the cost in 15 minutes or 10 minutes? So these AI tools like this one, which one of my students have developed, it is based on training of this one using 7,000 bridges that he designed and extracted the data using the tools that we have. And then based on that, this kind of a conversational tool is developed where you chat with the tool and it will give you the bridge options. And we'll say, okay, these are the options that fit your question. And then you can say, okay, this is the one that I want, this is I don't want. So it's not just one time answer. It gives you the options which you can explore, and then you can debate and you can improve. Once you're done, the data is transferred to our main program, CSA Bridge Express, and then the model is automatically created without any intervention. So no data has been entered, no file has been read. Everything has been automatically generated through AI tool, which first found out what parameters are needed, what is economical, and then generated the model, transferred, and then run the analysis to confirm. So this is how the AI-based engineering is that we are looking at now, that we can develop such tools which can provide us very quick, within 10 minutes, you can have all the information, including the BOQs and everything. So let's look at, now that we have discussed the background, let's take another look at how engineers learn and practice. And I'm going to go through a little bit fast because I think we don't have many audience with structural engineering deep practice. So I will not spend a lot of time. But basically, in the past, the process was sequential and hierarchical. We learned through a system, theory, then equations, then solved manually and apply in practice. Like I said, practice and education had the same level. And people had to have deep understanding of fundamentals, because without that, it was not possible to understand and apply those equations. Of course, limitation was time consuming, and then we had a steep curve, learning curve. And the example is this beam. Everyone remembers this one from the class. We have the formula for the bending moment. We had the tables. So that was all we had at that time. Some tables and some formula, and everybody used the same. Then some methods were developed like moment distribution for analysis, but this one's still very good because people developed clear understanding how the moments are distributed based on stiffness and so on. So they understood how an indeterminate structure will behave. And they had to do this step by step and complete all the steps by hand until we got the answer. So conceptually, it was very clear and it was reasonably accurate. Then there was this portal frame method, which was used in the uh, Empire State Building. And in fact, during that time, it was developed. And it was such a simple method which could solve a 100-story building. And based on certain basic and simple assumptions, the entire bending moments on every column and beam could be computed um, by hand, because the concept was so simple that you assume that the floor is cut, and then you have a point of inflection, and you have a shear there, and then from that shear, you calculate bending moment in the column. From column to beam, you do moment distribution, and very soon you can solve the entire building. Once again, simple, reasonably accurate, I would say, within for those kind of buildings, and it worked. But once again, everyone could use it. But now the typical project life cycle is very complex. We have so many steps, so many people have come in, things have become very complicated. And then we have, so structural engineering actually needs to support many of these project life cycle stages, including the end of life and the dismantling of the structures. You have seen many buildings, they put the explosives and explode them. And structural engineering is still needed to see where exactly that should be done. So including facility management and everything. So structural engineering and their role has expanded and can expand to several areas in the life cycle. And the design workflow is also complex now because of the projects. Like I mentioned, we have to do many things, and then it's an iterative process and takes a lot of time. Because of that, now the tools have become more powerful, but at the same time, less engaging or less understood. So now, for example, if I use ETABS for a project like that, a small building, then from ETABS, from the architectural drawings, we will make the structural plan, structural model, and we can get the, from there, the drawings. Previously, this could be done directly without calculation because there was no tool. So once you make this one, you do the hand calculation. From the hand calculation, you calculate this reinforcement and you make the drawings. So that was the past. But now you have to go through the whole modeling procedure in the program, enter so much data, assume so many things, create the model, then run the analysis, calculate bending moments, and we don't sometimes understand how all these moments were calculated, why they're very high and upon vacation, why they were low, because we run it almost automatically. From there, we check the DC ratios and we get the reinforcement cage, and from there we get back the details. So now the step which was short earlier is very long. Previously, there was a clear understanding how we got there. Now we have a kind of a long process going through the programs, and we don't really know often what happened and then what choices we made in the program depending upon the parameters that we use. So structural engineering still requires conceptual clarity, load paths, equilibrium, stiffness, failure modes, but modern learning often skips that. And the tools that we have are kind of black box. So we don't know how it was done inside because we can't have access to the steps of the process most of the time. And even if we do, it's just a lot of data, terabytes of data. So something needs to be done. That's what we are talking about now. So let's look at now the new generation, the current generation, Gen X and Alpha and others. There's a shift from theoretical solution to first learning behaviors. That means they would like to learn by doing first and understand later. They would prefer video, visual, and modular training. Look for demand and look for and demand answers rather than step-by-step derivations, and then expect instant feedback and interactive simulation. So as you know, we have this idea that everything should be quick, immediate, and within a few seconds because of the availability of all other tools that we see. And they often works across many tools, not within one deep specialization. They can do many things at the same time because all of that is available in AI. All of that is available on the smartphones and on internet. So they have access to a lot of connected and sometimes disconnected information. So now it's not just the students that have this attitude, but even the people, engineers are are forced to do this one because of the time constraints. So they have to follow the same procedure where they cannot have the deep understanding that they had earlier. So visual suggestion is very important for the new generation because they can look at many things. They work visually. They open many programs together. They look at many screens together. If you go to any office now, people have two monitors, three monitors, sometimes four monitors, and they are looking at large monitors. So they are looking at a lot of visual data which they are trying to sort of assimilate to solve the problem. It's not focused on one issue at a time. So many windows are open, so much is happening, and they learn to absorb all of that. So there is a lot of sort of advantage, but it's also disadvantage that there's a lot of loss of focus during that time. So learning is no longer linear; it's parallel, interactive, and adaptive. And it doesn't come from class, but come from multiple sources, and that's where we are sometimes lacking, that they have other sources to get the same knowledge or same information. So the teachers, their now dilemma is how can they keep the students engaged while ensuring depth, because the attention span is reducing because they are used to quick answers and quick sort of uh, work that they do on their devices. So the educators or teachers sometimes lose the interest of the students. The practitioners have to keep up with the tools which are developing very fast. The tools, the people who develop software have an obligation kind of to release one version every year. So they keep adding new options in the program, which the practitioners or the students have no idea or what they do and how to use them because it's just changing every year. The new version comes, and whatever they learn, they have to relearn and then they have to re-educate themselves. So now the solution is that we because these tools are here, so we have to use these tools to do our work. We cannot get away from them. So, but we can see from all of this to conclude is that the future of engineering is going to be hybrid, combining human insight and machine assistance. We cannot neglect that anymore, and this machine assistance is now only going to increase, as we can see from now. Learning will be continuous, modular, and AI personalized. So learning is not that we finished in school. We will have to continue to do that. And it will be in pieces, whatever we need, we learn that. And also AI can now personalize this learning. And that's going to be a major shift on how we work. And universities and companies are shifting towards micro learning and simulation-based training. And I'm going to talk about that today. So we have AI coming in and we have simulation, and we have all of that. So let's just see how this works. One more thing before I go to the examples is that the programming is coming back. When we were studying at that time, almost everybody learned Fortran, but there was a time in my class when I used to ask every time how many people want to learn programming, and that number reduced significantly in the last 10, 15 years ago. But now I find that once again, there is another interest in programming because we have AI-enabled coding, vibe coding, and no coding concept coming up. So anyone can write programs, and it's become very easy. No need to learn languages. and Python and the scripts are much easier. So now we see a lot of students now learning Python or use APIs or MATLAB or even Java, and especially learning to use AI-enabled coding. So this means that more people will be writing code for them, they're doing their work in whatever form. And that's a major change from the previous one because it's not just using tools, it's also developing your own tools. Like as you know, agentic AI is now, the term is popular, that people will write their own agents using AI, which can do work for them. So which means that we will be now not only engineers, but also kind of programmers in some way. So now let's demonstrate these things from some examples. Uh, and the first thing that I want to emphasize is that the learning, we have to see a pipeline. So any or all of them could be used, or a group of them can be used. So theoretical concepts, development of equations, derivative equations, response visualization through graphics, and then animations and numerical simulation through software, and then physical demonstrations. So a combination of these will have to be used in a kind of a circle. So each will reinforce the other. So these will become pillars of effective learning experience. Manual calculation will be required to build foundations, physical models and experiments, and then numerical simulations and interactive visualization, like all of these interactive immersive devices, for example, VR and MR and all of that things. So the advantage will be that students learn faster, teachers can demonstrate effectively, and graduates will become practice ready. So let's look at some of the ideas here. So these are just some of the examples that I'm going to give you. For example, we as engineers, we learn the stress, equation, and we say, okay, this will vary with height, with y, and so on and so forth. But if you visualize it or if you animate it properly, of course, we can have physical models. I remember our professor used to bring a foam beam into the class and bend it. And now we can do a similar thing through the animation. So this was done in some people in my office. And we can see where the neutral axis will be. We can see the tension. We can see the compression. We can just understand all of the concept in one go rather than through 2D diagrams trying to visualize how this will work. For example, how the tension and compression will work with the moment and so on. So this kind of combination of equations, then combination of some sketches, and combined with animation can provide a significant deep understanding. And once you have it, then it can be on YouTube and so on, and people can watch it. So this is the first thing, that we can combine these two together. The next one is physical. So here, if you want to see how a frame deforms, for example, this device called Mola Structures has now become quite popular. Many universities are buying it. People are building it also. You can also create by yourself. And you can see here that left-hand side on the top is this model. Then you have the deflection shape from the analysis, and you have the shear force and bending moment diagrams. And then let's see how the physical can work. So let's say for the vertical load, you can see how the deformed shape will work. And similarly, for the lateral load, you can have the animation, and you can see how the animation will work, how the bending will deform, then shear force diagrams plotted on that, and similarly for bending moment diagrams plotted on the same diagram. So now we can have multiple ways of demonstrating this concept. Similarly, we can do that for the lateral loading, and we can add more information there. For example, you can say where's the rigid joint, you can show animation and the physical side by side, also the analysis, and you can say what is the displacement and where is the zero rotation, and we can then animate them and clearly mark on the physical model. So combination of physical model and animation can make these concepts clear, much better than simply explaining them through presentations. Similarly, for the dynamics, for example, we normally would like to show how the natural period varies with the stiffness and the mass. So this is an example where you can make a physical model, and you can see how the ground motion of different frequency will excite structures of a certain natural period. And you can also do the same thing. We can also do the same thing from the programs like SAP also can show the similar. So we can do simulation, and we can use physical demonstration, all combined together, giving together with the formulas. And similarly, if you're doing the simple analysis, you can show the tools and the equation side by side, so people can correlate this, and they can verify these things quickly from the program with the calculation, so that there is side by side comparison for learning that this is the equation, this is how it looks like, and this is the program. So you can learn and verify your computations, or check the program accuracy. So another thing, normally, this is a sketch that is a very long time ago I made when I was working in Progressive Consultants in Lahore, on the modeling of the foundation. At that time, we just modeled the foundations like a pin or a roller. But I realized that was, people realized at that time also that the real foundation is none of that. So it's more like a spring. But the idea was, how can you model that? So this was wrong, this is right. But the question is, how can you demonstrate this to the student? Even now, many people continue to use this assumption of fixed pin foundation rather than the real behavior of the structure. And in fact, real behavior is far more complicated, but even the simpler application, many engineers do not uh, see that. And this is just a quick comparison that if you use the pin support, what will happen to the bending moment at the foundation if you use a fixed support, and what will happen if your foundation soil. So this can be, I'm sorry, the title is reversed. This should be fixed. So because of the software and tools that we have, and easy to visualize tools, we can quickly compare how the results will vary when we model the foundation in different manners. So let's look at a project and go and look at a few more tools uh, from there. So this is a small school project that one of our team member in the office made this plan. Uh, so the idea is that the students, they should be shown first what they are learning, what they're going to design, what it serves, what is the purpose, and why it is important that you're designing something which is going to accommodate the children and is going to be for safety and so on. So we start with that level, give them the picture uh, of the project they're doing and its significance. And then from the architectural drawing to understanding of how the various three-dimensional, two-dimensional systems work, and from there to be able to read the basic drawings, understanding where the beams are, where the columns are. So we start at the top rather than start with the beam design first. Explain to them why this design is needed, and why the bending moment is important, and why the earthquake or the wind are important. So that information normally should be given first. But when we study at the very low level, we don't know what the application is. So that's one of the change, I think, that will help students learn better. So once we have that, then we can use either the integrated way, the ETABS way, the way you can model the entire thing, and I showed you earlier, and we can come to the final design, or we can teach them to do it step by step by themselves and not use the programs which are kind of black box. So that's the next change for learning. So using step-by-step approach is that they do the same project, but don't use the software uh, like blindly. They do this project step by step with the tools, with the help of the tools, so that it's still faster and they know how to use the tools and they understand, but do the problem by themselves, formulate the problem by themselves. So they should know that, okay, this is the plan. I am going to have frames in this direction, frames in this direction. I'm going to calculate the load like this. So we start from that concept. Don't let the program automatically create the frames or create the loads, calculate the loads. Do this part by hand, for example. Then explain how the beam analysis will work. This is a tool that we are developing. for the beam analysis, so they can enter all the data from that project. So they know that they have taken one beam, they've calculated the load, and then they apply here by hand. And then, of course, the analysis can be done by the program, and it can give the bending moment and shear force, everything that we need. So that part is okay. But creating the model, applying the loads, understanding how it works should be done by these students, and so that they have developed the understanding. Then we can take them to design that how this bending moment will take from here and transfer to a table where all of the bending moments are collected from all of the beam, and they can see and select one of the row, and then they can do the design. And this design I will show you a little bit more in detail, that they can then go into the details of the design of the beam. So once again, the beam is not automatically designed. They have to pick one beam location, and then they say, okay, this location, I want to design this beam. This is where I found the maximum moment, and I will design it. And that's how we can teach them how to do the model, how to do the analysis, and how to link the analysis to the design. And similarly, we can do the horizontal load or lateral load analysis for wind and earthquake. Same way, they can calculate the wind load by hand, calculate the earthquake load by hand, apply to the frame, and then run the analysis to solve it. Because now we have tools, they don't have to do the analysis by hand, but at least the steps should be done by hand. So we have this, they understand how the bending moments are working, or the shear force is working, and so on, or the deflection shape is working. And then they can combine this lateral load moments to the beam by themselves, rather than an automated handling of gravity load and earthquake loads. So this way they will understand how the bending moments transfer from earthquake to the gravity loads and how they combine, and then how finally we can use them for the design of the gravity and earthquake together. And so this is the advantage of step-by-step learning with understanding, but with the help still using the tools. So the comparison can be shown that, okay, this is the gravity load, this is the lateral load, the reinforcement is added for earthquake. So they can easily see that this was the reinforcement without earthquake, this is the reinforcement with earthquake, and so on. So this kind of comparison and this kind of studies will help them to deeply understand what they're doing. Another area where tools can help is to show how the capacity of the section will become minimum reinforcement, singly reinforced beam, doubly reinforced beam, and insufficient section. So we can simulate this situation, and they can see, okay, this is the moment, minimum risk governing. If this is the moment, then the singly reinforced beam, and then we have doubly reinforced beam, and then no solution is possible. So we can show this through the program here. And in this one, in this tool, you can see that once they increase, they can also see, once they do the design, they can also see the details, but they can also see the flowchart, how the program worked. So it's not a black box. They can see the program followed these steps, and this is how it calculated. And the calculations are also presented in the same way. And they can see, okay, the program followed this path when I used the bending moment in this range. Then we increase the bending moment, and then once again we check the results and go back to flowchart, and then we can see that the program now followed a different path and calculated different things. So this combination of the program's internal expression of the process is very important to make it black box, make it transparent, and also to explain how the program reached that level. This increases the reliability and also the understanding. Similarly, we can do for shear design. We have the regions for shear design, no reinforcement, minimum required, some required, and then section is inadequate. And same way, the program, the tools can help to identify those, show the calculations, and show the flow chart, how the whole thing works. So you can see here that the shear, different value of shear will take the program to different paths. And then the calculations are also detailed. That means each equation is written and then the numbers are substituted and the final results are calculated. So it's not that we don't see what the equation was, what numbers were substituted, and how the calculations were done. So it's very easy now to cross check. First of all, easy to understand what equation were used with a reference to the code, and also what numbers were used and what value came out. And this, and together with the notations and everything. So if the calculations are presented from the tools in this way, they are as good as manual hand calculation because they follow the same process. But because we have many equations, many beams, they can be done faster. And more importantly, the parameters like cost and sustainability metrics can be added to the same tool. Because engineers, as you know, as I mentioned earlier, that's our job, safety as well as sustainability. But our normal programs that they work in engineering for mostly they don't calculate the indicators that we need, for example, embodied carbon, and also the cost and quantities, which are easy to compute from the same data that we already have. And we can also study the equations um, parametrically. For example, we have this equation and we can say, okay, I would like to see how does the plot of the equation look like if I vary this number and I fix this number. So this is the plot of this equation with this numbers fixed and this numbers varied from here to here. So you can generate graphs. We can see how the equation performs because a lot of the time students do not understand what the equation is doing and what is the significance of the parameters in the equation, which are significant, which are not. So these tools can help to uh, bridge that gap. And on top of that, similarly, I will just go, give you a few more examples of the tools. So we can have tools, we can do the truss analysis. Similarly, they can show the forces in the truss, they can do the design. So these tools are now specific for each type of problem rather than one big integrated tool which can do everything. And those tools are very good for large projects. And once the students have mastered the learning and they have understood, but they are not good as learning tools. So what we are trying to do is to develop tools that provide the learning and practice at the same time and integrate that. But the learning and practice are done kind of step by step. So similarly, this is a tool for frame analysis, and people can create different kinds of frames. They can analyze it, study the behavior, and then transfer this data to the beam design and to others. So one of the advantage of these tools is that if you see on the right-hand side, those are the sub-tools where the data can be transferred. So rather than doing this thing in one step like a black box, we let the engineers or the students do the one work and then activate other tools to transfer the data and see how they work together. So that's the right-hand side is the integration part. And similarly, if they're doing the column design, they can study the interaction surface and they look, points on the interaction curve and so on with all the numbers. And foundation design, same way. So if they want to design the foundation, we have the similar tool. They can vary the soil parameters and the load parameters, and they can determine the design from there. On top of that, sometimes the practical design does not require them to have a deep understanding of stress distribution. And this is often missed. So the tools like this one, if they are doing a beam, they can also transfer the data to a stress uh, computing tool, which gives them calculates the stress at the cross section as well as along the length, and also uses Mohr circle to show the interaction between shear and the flexural stresses. And then also, you can see the distribution, and they can also see the uh, vectors of the principal stresses. So this one tool gives a very deep understanding of what's happening in a beam. So the students or the users can change that slider and then study the beam at various locations along the length. For example, let's look at this example. So if we transfer one of these beams from that model here, and then we can just see that we move the pointer, and we can plot any kinds of stresses. We can move that here, and then we move the pointer here, and we can see the Mohr circle. We can see the principal direction of stresses from shear and axial stresses at any place in the beam, both in the cross-section depth and along the length. So this kind of visualization tool, interactive visualization tools, can teach about the basic concept far better than the equations. And of course, equations are also available, as I showed you earlier. Similarly, we can go to nonlinearity and demonstrate how the moment curvature of a beam changes by confinement, by reinforcement, by this one. And once again, we can see the stress strain plots of the material. This is the steel stress strain plot. Then it's a concrete, unconfined concrete outside, and that is the confined concrete inside. So we can have a confined concrete within the core, unconfined concrete outside the core. Students can change the parameters of the stirrups and so on, and immediately see how it affects the ductility, how it affects the stiffness, and so on. So that's the difference between a tool designed purely for design and a tool designed for learning and design. One more similar tool is for understanding the dynamics. Like this is for single degree of freedom dynamics, free vibration. So users can change something and they can see how the damping works and how the vibration works and what is the initial period, what is the frequency, and so on and so forth. And they can see the animation on the right-hand side. And this will supplement the diagrams and the physical model that I showed you. Same thing you can do for periodic vibration. So we can study those effects by live through these tools. So I just give you some of the examples of what can be done now that we have all these technologies available to us. So we can use those technologies to develop these tools to actually provide better learning experience for students and for the practitioners to get a deeper understanding. So let me now just conclude. Basically, the physical infrastructure, this is, if you ask any AI program and say, give me a future state city, then it will give you all kind of future infrastructure. And which means that even future vision of humanity is still advanced infrastructure. So if that is the case, that means our field, our discipline has a long way to go. Because as we proceed, the infrastructure is only going to get more complicated. It's going to get more sophisticated, which means the civil engineering will still be relevant, very relevant. Structural engineering will need to adapt, will need to learn to be able to design all these infrastructure projects. And we can see clearly that human intelligence and artificial intelligence will have to go together in this learning and practice time that we are looking at. So technologies will not replace engineers, but it will redefine the work we do and how we do it. So people will focus more on the framing of the problems rather than solving the equations that I've shown you through many tools. So now it's important that we frame the questions well. We know what we're looking for. We look for the why, and we get the answers of how in return. So with that, I will just say that although the tools are changing, but our mission of the engineering, of the civil engineers and structural engineers remains the same, which I mentioned right in the beginning, was to reduce the disaster risk by reducing the vulnerability of built environment with due consideration to sustainability. So that brings us to the conclusion. I went a little bit fast, so that we have more time for questions, and I can always go back and show things in more detail. So thank you so much.
Thank you very much, Dr. Saab, for what should I say, for such a unique and illuminating session on innovative tools for enhancing engineering education. And I just want to, before we go into the questions, I just want to make one announcement. I'm sorry, there were some technical issues not at our end. Uh, you see, we are monitoring our broadcast on Facebook and on Zoom at two independent stations, and nothing was reported there. But we did had some phone calls from the people who wanted to join, who were registered and they couldn't join. I really don't know where was the problem, and I cannot answer the question at the moment because certainly the problem was not at our end and not at the end of our speaker, because we were getting his broadcast very clear and very crisp. So what I can do is that this today's session has been recorded and it will be uploaded in a day or so on our website. Usually it takes 3 to 4 days, but we will do it quickly since some people were interested and they could not join us. So for their convenience, we will upload this today's session in a day or two. So, Doxa, we have two questions. So one question is very important. I think it has been asked by Arsalan Salim, and that is since ACI and other design codes focus on structural safety, not AI outputs, are there any global guidelines that specifically address how to verify or cross-check AI-generated structural analysis results? So in future, how this issue will be taken care of, Dr. Saab? Please answer.
Yes, absolutely. I think this is a question that I get asked almost all the time from every presentation that I make. And to me, the difference between using any other tool, for example, ETABS or SAP or anything, and AI is not much different. It's still a tool because these software, commercial software, can also make mistakes. And we have to check and verify the results because ultimately the responsibility of delivering a safe structure is ours, not of the tool. So AI is once again exactly the same. It's just another tool. It's a better tool. It's a faster tool. It has more options. But in the end, we must verify this through our understanding, through through I would say an alternate way of doing that. So that responsibility will never go away, and we will never be able to say that I got this from AI. It's not my responsibility, and no client, no government will accept that. So I think to me, we should keep in mind that AI is always going to make mistakes. We should start with that assumption. It can help a lot, but we must have a habit of cross-checking it. And there are many ways to cross-check. That's why the understanding is important. You can cross-check by some simple thumb rules. You can do some simulation to cross-check that. But one thing that I want to mention is that the AI, which is commercially available, and the AI, which are being developed by engineers for engineering problems, are slightly different. If you ask the same question to ChatGPT, and if you ask the same, like for example, the bridge example that I gave you, where you can ask the program to design a bridge, you cannot ask ChatGPT to do that, not yet, and probably not for a long time. But this tool that we designed or we developed was actually trained on, like I said, 8,000 bridges that we designed and verified before we used that data to develop the tool. And it still, after the initial estimation, it still carries out the finite element analysis and design and goes through the code check and only then gives the answer. So the AI tools should never give the final answer. They should give us the preliminary sizing. They should give us the prediction, or they should cross-check our work to say, okay, this looks okay based on my previous experience. So I think that's how we should look at AI. Never for answers, but as assistance to help us.
Yes. Thank you, Dr. Saab. I was also of the same view that we should, for the time being, we should continue using our standard softwares for designing longhand calculations and only use AI to cross-check our work. I think that would be the better policy for the time being. And Arsalan Salim is a very young engineer, and I'm happy he has asked such a broad question and a very pertinent question. Now, the question first, before Arslan Salim, since this question was pertinent, I asked it before this question that was asked by Parvez Nashai Sahab. Dr. Saab is saying, Parvez Nashai is saying, I am master's. Uh, just a second. Just a second. My master's thesis on Trivela Dam. I used FEM model and worked at AIT Computer Center. Is FEM used in structural engineering is outdated? Basically, he's asking, is FEM method now outdated? I don't think so, but Dr. Saab, please answer the
No, no,
question.
no. I think FEM is the only, in fact, method that has survived so many developments over the years, and it has almost become, I would say, so many other methods came and have come and gone, but FEM has still survived, and I think it currently this is the de facto method for analysis. It has become very mature, and it has become very stable. So I think the FEM solvers or the engines have become very standardized, I would say. So I, is this the? I don't think FEM is going anywhere very soon.
Yeah, I also agree with you that it won't go anywhere soon. So AI, I mean, relying on the AI and AI doing some design work, I think still it's a long way, but you don't know the way the technology is progressing and with the speed.
Yeah.
Maybe
Yeah, so I
it
was in
can.
a, yeah, 2, 3 months ago, I was in a conference, and in fact, the first international conference on AI in structural engineering was held in Turin in Italy, and I also attended that. And almost, most of the top experts in this area, who are working, were presenting there. And I looked at all of the work that people were presenting, and almost none of them is actually geared towards final design output yet. They're all
Mhm.
towards, uh, you know, uh, for example, crack detection. Somebody's doing that. Somebody's working on preliminary sizing. Somebody's working on optimization. Somebody's working on cross-checking of the results. So things like that. So I think that's where AI will be best used as an assistant in the workflow.
Okay, so we don't have any further questions, but Dr. Saab, I mean, your talk was a bit unique and innovative. Maybe people will go on this lecture again and again, and they might ask some questions that will come to their mind. So maybe Sadhya will send those questions to you later, and
So
I'm pretty sure you will be happy to answer them.
absolutely, absolutely,
So
Smith, my pleasure.
again, I thank you very much. Your thoughtful exploration of emerging technologies uh, and their integration, I think, has created a pedagogy challenge for the teachers and those who are in the education. That what will be in future, what will be the method of teaching, and how this challenge has to be dealt. So I think you have your deep insights drawn from decades of global experience will force all of us to give deep thought to the future teaching methods in the engineering institutions. Just
So
your final note on it, and then I will thank you again. Yes,
So
Dr.
what I presented to you, those tools, is actually something that we are working on at the moment, and we hope to create a platform for this. I think it's very soon. So we will launch this, and we hope that the universities will use it, and we will try to make that available to most of the people, widely. And we believe that will start to help moving in that direction. So currently we are working on it. So most of this work that you saw is our work currently being done at AIT at CSA Bangkok that we will see in the future. So
Of
thank you so
course.
much for inviting me.
No, it's always our pleasure and our privilege to invite you on this forum. In fact, you are a experienced engineer, and everybody learns from you, from your experience of 4 decades, spanning over 4 decades. So I look forward to continued engagement and collaboration uh, as we collectively strive to build a more informed, capable, and future-ready, what should I call it? A future-ready engineering community. So thank you very much, Dr. Saab.
Thank you.
Just
Thank you, everyone.
before concluding, I have to make some announcements. Next lecture is on 13th December 2025. The topic is seismic analysis and design of 249-meter high Dariner Arch Dam in Turkey. And our speaker would be from, I don't know, he's going to deliver the lecture from Switzerland or some other place in Europe. The speaker is Dr. Martin Wieland. I think Dr. Nadeem, you might be knowing him. He has
He was
been
my teacher.
also.
Yes, yes. Dr.
Yeah,
Martin Wieland
yes.
is, he's a very good friend, but he was my professor at AIT, and he taught us
Uh,
bridge design at that time. Dynamics of bridge design I learned from him. So he's still
I
in
see.
touch, and he has done a lot of work in Pakistan. He has
Yeah,
worked on
yeah.
many dams.
So next time on our screens on 13th December, he would be there to deliver the lecture, same time, 2 p.m. Pakistan time. And all the audience today who attended today's lecture and were registered, they can collect their certificates on from Thursday, that is 20th November onwards, from our office, 14A1 Block P, Moreton Extension, Lahore. The contact person is Ahmed Akram, and his telephone is 0347462511. So you are most welcome to call him before coming. And Dr. Saab, again, thank you very much. And before closing, I would like to thank my IT team who works hard behind the curtains to make this broadcast smoothless and a quality broadcast. Thank you very much. And I will see you on 13th December 2025, which will be the Saturday again. And God bless you. And remain happy where you are. Thank you very much. Dr. Saab, Khuda Hafiz. And Dr. Saab, your shield will be sent by DHL or by any other post, courier
I
post.
think I will give her the address in Islamabad, and it's best that she sends it in Islamabad. So I will let her know.
Okay. That
Yeah.
again, it will reach there wherever whatever address you have given. Inshallah, in next 2 to 3 weeks, it should be with you within 2 weeks. Thank you very
Thank
much,
you.
ji.
Thank
Allah
you.
Hafiz all. Stay safe.
Allah Hafiz.